We are going to do our Unit 5 notes today over temperature and thermal equilibrium. This is Chapter 3 in the textbook. Please make sure you have the notes from the bin, the notes that you will be filling in the blanks and highlighting as we go. All right, this first slide I'm going to read. You are not going to do anything on your notes for this first slide. So, kitchen objects. Carla took a thick oven mitt, a metal baking tray, and a plastic bowl out of the kitchen cabinet. She set the objects on the kitchen counter and waited for her friends to come over to bake cookies. Carla and her friends had different ideas about the temperature of the objects. Which student do you agree with the most? So let's read through the students. Carla, I think the temperature of the oven mitt is greater than the tray or bowl. Jasmine, I think the temperature of the metal tray is lower than the oven mitt or bowl. Nina, I think all three objects are the same temperature. Patrice, I think all three objects are at different temperatures. Okay, so who do we agree with most? The best answer was Nina. All three objects are under the same conditions. No heat is being transferred between the objects, the air and the kitchen counter. They will all be the same temperature, which is room temperature. So they're all going to be the same right now and be at room temperature. All right, again, I'm just going to read this slide. So kinetic energy is energy an object has because it is moving. Potential energy is a stored energy. Temperature is the average kinetic energy of the particles that make up a material. As the temperature of the material increases, the average kinetic energy of the particles increase. Heat is a movement of thermal energy from a warmer object to a cooler object. So it always goes from warmer to cooler. When thermal energy moves between a material and its environment, the material's temperature changes. Heat continues until all objects in the contact are the same temperature. This state is known as thermal equilibrium. So when they're all the same temperature, we have reached thermal equilibrium.
How does thermal energy cook food? Let's find out.
Okay, take a second to fill in the blanks and highlight or underline the parts on the screen right now. So you are writing down motion on your sheet of paper and you're highlighting how warm an object feels depend on how much kinetic energy its particles have. And then you're filling in the blank for kinetic energy, and then you're highlighting or underlining the ability to cause change. Energy and temperature. Particles and motion. Every solid, liquid, and gas is made of particles, and their motion is related to the energy a substance has. How warm an object feels depends on how much kinetic energy its particles have. For example, even particles in a solid object are moving. A hot cast iron pan has particles vibrating quickly and moving more quickly than a cool one that has slower moving particles. Kinetic energy. Kinetic energy is energy due to motion.
And now for the Texas pledge. Honor the Texas flag.
A moving soccer ball and all their particles and hot maple syrup both have kinetic energy, the ability to cause change.
And now for a moment of silence.
It can take different forms, including thermal energy, electrical energy, radiant energy, which is light, mechanical energy, and sound energy. All right, so looking at these pictures, examine the images. Where can you find kinetic energy in your everyday life? All matter is made up of particles that are in constant motion. Depending on the type of matter, the particles may be atoms or molecules. All moving particles have kinetic energy. So looking at the gas stove, the moving gas molecules from the burning fuel have kinetic energy as they spread out and collide, producing heat and light. For the violin player, the moving bow and the vibrating strings create kinetic energy which produces sound waves. The toaster oven, the moving electrons in the heating wires and all the molecules inside the toaster as they heat up and move faster contain kinetic energy. The light bulb, the moving electrons in the electrical circuit and the vibrating atoms in the heated filament have kinetic energy, which produces light and heat. So they all have kinetic energy. Okay, take a second or pause the video to fill in the blanks and highlight the section here that's highlighted. The greater the average kinetic energy of particles is, the greater the temperature. Okay, temperature. Scientists define temperature in terms of kinetic energy. Temperature and kinetic energy. Temperature is a measure of the average kinetic energy of the particles in a substance. The greater the average kinetic energy of particles, the greater the temperature. If particles are moving fast, the temperature is higher. So, the faster the particles are moving, the hotter the item will be. In a warm house, air particles move faster, have more kinetic energy than that particles outside when it's cold. On a cold winter day, the inside air has a higher temperature because the particles move faster compared to the colder outside air. Temperature scales. Temperature can be measured using different scales. So these are the different units that we use. Fahrenheit, used in everyday life. Celsius, which is used in science. Kelvin, which is also used in science. So the units, Kelvin and Fahrenheit and Celsius. These are all the different degrees. All right, so temperature scales. If you want to bake a loaf of bread, it is important to know exactly what temperature to set the oven. Many processes in chemistry also depend on temperature. So the Celsius scale is based on the freezing point and the boiling point of pure water. So it freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. The intervals on the Kelvin scale are the same as those on the Celsius scale, but 0 Kelvin equals negative 273.15 degrees Celsius. 0 Kelvin is known as absolute zero. You might have seen one temperature in a weather report given in degrees Fahrenheit and degrees Celsius. On the Fahrenheit scale, water freezes at 32 degrees and boils at 212 degrees. On the Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. The Celsius scale is used by scientists worldwide to convert the Celsius to Fahrenheit using the equation. So this is equation to convert Celsius to Fahrenheit. To convert from Fahrenheit to Celsius, you would use the following equation. Room temperature is considered around 72 degrees Fahrenheit. Convert this temperature to Celsius. Okay, so we'll take 72 degrees Fahrenheit, subtract it by 32, and then times that 5 divided by 9, and that equals 22 degrees Celsius. So you just plug it in if you're calculating for Celsius. Okay, take a second to fill in the blank for movement. So look for particle and temperature on your notes, and then go down to the last two sentences and highlight or underline them. All right, particle movement and temperature. 3 drops of dye food coloring are dropped into a beaker of 20 degrees Celsius water and 80 degrees Celsius water. When first put into the beakers, the dye particles are close together. Water particles, like the particles in all liquids, constantly bump and flow past each other randomly. The movement and collision of the water particles push the dye particles all around, causing the coloring to spread out or diffuse. Particles diffuse until the dye particles are evenly mixed with the water particles. Consider the dye particles after some time in 2 beakers. The beaker with a higher temperature has particles that are moving more quickly and bumping into the dye particles more often. The faster the particles are moving, the faster the dye diffuses due to greater kinetic energy of the particles. Temperature and kinetic energy are directly related in terms of particle movement, which is why the dye spreads out in the warm beaker. Compare. Examine the image. Which beaker has particles of more kinetic energy? So do we have one with 20 degrees Celsius and one with 80 degrees Celsius? The beaker on the hot plate has particles of more kinetic energy. Every object is composed of particles that are always in motion. Temperature is a measure of the average kinetic energy of those particles. The faster the particles move, the greater the kinetic energy and the higher the temperature. So the particles move faster because there's more energy in the particles. What is the relationship between particle movement and the temperature of a substance? The higher the temperature means the particles have a greater average kinetic energy, so they move faster. Air fresheners are placed in 2 rooms. The temperature in the first room is 20 degrees Celsius. The temperature in the second room is 25 degrees Celsius. Which room would feel the scent of the air fresher first, and why? The air particles in the 25 degrees Celsius room have more energy, so they move faster than the air particles in the 20 degrees Celsius room. Energy of a substance is affected by 3 main factors: number of particles, states of matter, and type of matter. Since thermal energy depends on various factors, temperature is not a direct measure of thermal energy. Does the thermal energy of a substance always increase if the temperature increases? Yes, an increase in temperature indicates that the kinetic energy of the particles increase, so the thermal energy must increase also. What are two ways the thermal energy of a substance can increase if the temperature remains constant? If the object changes from a solid to a liquid or from a liquid to a gas, the change involves an increase in potential energy, so the thermal energy will increase, but the temperature will not. If the amount of substance increases, since temperature is an average, it can stay the same, even when the total kinetic energy increases, because there are more particles. All right, we're going to watch the video.
People all over the world love to drink tea. There are hundreds of flavors of tea, but traditionally, a cup of tea starts with the harvesting of leaves from a tea bush. So, how do we get from this to this? Have you ever left a jar of water with tea bags out in the sun? As the sun warms the water in the jar, the temperature rises. This causes the particles in the jar to speed up, which mixes the water and tea particles. However, it takes a long time to make sun tea because the water particles aren't moving around very quickly. But eventually, the tea particles will mix thoroughly with the water. Now, all you have to do is add ice and enjoy. If you don't want to wait for your tea to brew in the sun, there's a faster way to brew it. Just use hotter water. After tea leaves are harvested, they are dried out and ground into small pieces. Those small pieces can be placed into a tea bag. To make tea, you place the tea bag in hot water and let it steep for a while. You can see that the tea bag is motionless. So what is causing all the movement inside the cup? Why are the tea particles mixing with the water particles? If you could zoom in on what is happening in the teacup, you would see that the particles of water are moving very fast. The hotter the water is, the faster its particles move. Hot water brews tea more quickly than cold water. Because the water particles are moving fast, they bump into the tea particles, causing them to move around as well. Eventually, all the tea particles will mix evenly with the water particles. Your hot tea is now ready for sipping. Why is tea such a popular drink? It depends on who you ask. Some people drink it for its health benefits, and some people just like the way it tastes. And some people find that it tastes even better when you share it with someone else.
Okay, take a second to fill in the blanks and highlight what is on the screen. If you need additional time, you can always pause the video. Okay, now we're going to talk about thermal equilibrium. Particles that make up any object not only have kinetic energy, but they also have thermal energy. So thermal energy is the total energy due to the motion of particles in an object. The temperature of a substance is related to the average kinetic energy of the particles that make up that substance. Number of particles. The more particles an object has, the more thermal energy it contains. A bathtub of water at 20 degrees Celsius contains more thermal energy than a glass of water at 20 degrees Celsius because it has more water particles. Compared to a tablespoon of boiling water, a bathtub contains room temperature water is perceived as relatively cool, but the bathtub still has more thermal energy because it contains more matter. State of matter. As a substance changes state, its thermal energy changes. So our states of matter are solid, liquid, and gas. So a solid has less thermal energy than a liquid or a gas. A liquid has more thermal energy than a solid at the same temperature. And a gas has more thermal energy than a liquid or a solid. So gas has the most thermal energy, and those particles can move the most as well. Type of matter. Different substances have different amounts of thermal energy due to the type of particles that make them up. Thermal energy depends on the type of matter that makes up a substance. Why do you think there are more curved lines around the water particles than around the pasta particles? The liquid water has more energy than the solid pasta. What is it different about the particles that have only a couple of small arcs around them and those that have many arcs? So these arcs compared to many arcs. Fewer arcs, so like the pasta, indicate that the particles are not vibrating as rapidly. They have less kinetic energy. More arcs indicate the particles are vibrating faster. They have more kinetic energy. This means the water has greater thermal energy. So these little arcs, these little lines, means that they're moving and they're vibrating faster and that they have more kinetic energy, which means that they have more thermal energy. So a liquid would have more thermal energy than a solid. Identify which has more thermal energy, the molten metal or the container, and why. So the liquid or the solid. The molten metal has more energy because it is a liquid and has faster moving particles than in a solid, meaning higher thermal energy. Okay, take a second to fill in these 3 blanks, heat, warmer, and cooler, and then you need to highlight or underline the last 2 sentences. Okay, heat. Heat is a transfer of thermal energy from a warmer object to a cooler one. It always goes from warm to cold. For example, when holding a hot cup of chocolate, thermal energy moves from the cup to your cooler hands. Just as thermal and thermal energy are not the same thing, neither are heat and thermal energy. I read that wrong. Just as temperature and thermal energy are not the same thing, neither are heat and thermal energy. All objects have thermal energy. However, you heat something when thermal energy transfers from one object to another. How are heat and thermal energy related? Thermal energy is the total energy of the particles in a material. Heat is a transfer of the energy from a warmer object to a cooler object. So heat is going from warmer to cooler, and thermal energy is the total energy of the particles in a material. What is the direction of heat between a glass of juice at 5 degrees Celsius and air at 35 degrees Celsius? Thermal energy will move from the air to the juice, warm to cold. Okay, take a second to fill in the blanks and highlight what is on the screen. Okay, thermal equilibrium. Thermal equilibrium occurs when two objects in contact have the same temperature. The rate at which heating occurs depends on the difference in temperatures between objects. Thermal energy moves from warmer objects to the cooler one until both objects reach the same temperature. So, for example, if you have two beakers of different temperatures, one warm and one hot, the thermal energy moves from areas of warm to cold. This means the beaker transfers thermal energy to the air, which allows the temperature in the beakers, but the air warms up in return until all substances within the systems reach thermal equilibrium. During this time, particles transfer kinetic energy back and forth, colliding with each other. It is not possible to make something colder by adding coldness to it. A substance can only be cooled when some of its thermal energy is transferred to a substance at a lower temperature. For example, in a freezer, thermal energy moves from the water in the air until the water cools enough to freeze and form ice. Okay, effects of mass. Take a second to fill in the two blanks and highlight or underline on your sheet of paper. All right, effects of mass. When objects with similar masses but different temperatures are in contact, thermal energy flows from the warmer object to the cooler object. Thermal energy flows until both objects reach a temperature between the starting temperatures of the two objects. When an object is in contact with a much larger object, the larger object's temperature changes may not be noticeable. During the process of thermal equilibrium, energy is conserved. The total amount of thermal energy in the system remains the same, though it may be redistributed. All right, so let's look at this example of reaching a balance. A candle burns liquid wax that forms a pool around the wick. Liquid wax runs out of the pool and down the side of the candle. First, as hot liquid wax drips down from the lit end of the candle, it loses thermal energy to the cooler solid wax before it. The solid candle wax is relatively cool. Next, the melted wax will keep losing thermal energy and its temperature will drop. The solid candle wax absorbs some of the thermal energy. It gets slightly warmer, but not warm enough to melt. Third, the melted wax drops, hardens, and continues to cool until its temperature is the same as that of the solid wax below it. The drop and the underlying wax are both solid. The system has reached thermal equilibrium. Okay, let's look at this example. Getting ready for school. Kevin puts on hot soup into a food container. At lunch, he discovers that his soup is not warm anymore. What happened to the soup in the container? And explain. Thermal energy transferred from the soup to the rest of the room until it was thermal equilibrium with the air. So until it was the same temperature as the air. What happens at the particle level at the boundary between a warm object and a cooler object that are in contact before they reach thermal equilibrium? Kinetic energy of the particles of the warm object are transferring energy to the particles of the cool object. What happens at the boundary after they reach thermal equilibrium? Kinetic energy is still transferred back and forth between the particles of the two objects, but there is no net change. Okay, let's review thermal energy transfer. Thermal energy in an object depends on three main factors. Okay, so the thermal energy depends on its temperature, its mass, and its specific heat capacity. Okay, so thermal energy in an object depends on three main things. Temperature, the higher the temperature, the more thermal energy the object has because its particles are moving faster. Mass, a larger mass means more particles, so even if two objects have the same temperature, the one with more mass has more thermal energy, just like the bathtub versus the boiling water. Specific heat capacity. Different materials store different heat differently. Substances with a higher specific heat capacity, like water, require more energy to increase their temperature, so they hold more thermal energy at the same temperature. Okay, so imagine you have a cup of water, 200 milliliters at 50 degrees Celsius, and a bathtub full of 200 liters at 50 degrees Celsius. So we have a cup of water with just milliliters, so we have a little bit less, and then we have a bathtub, which is 200 liters, so a lot more. Both have the same temperature, meaning the water molecules are moving at the same average speed. However, the bathtub has way more water, more mass, meaning it contains far more moving particles than the cup. As a result, the bathtub has more thermal energy than the cup, even though both are at the same temperature. Okay, now let's take a look at an example of specific heat capacity. So imagine you have a metal pot and a plastic bowl, both at 30 degrees Celsius. Even though they have the same temperature, the metal pot has more thermal energy than the plastic bowl if it has more mass. This is because thermal energy depends on both temperature and the amount of material or mass. Also, different materials store heat differently. Metal conducts heat better than plastic, so it might feel warmer or cooler depending on its surroundings. How does a system reach thermal equilibrium? Thermal energy is a transfer between objects at different temperatures. When all objects in the system are at the same temperature, the system is in thermal equilibrium. So when they all reach the same temperature, we call that thermal equilibrium. So when your hot soup that you bring to school gets to room temperature, it is now all the same temperature, so we have reached thermal equilibrium. How does a system reach thermal equilibrium? All particles are constantly moving and have some kinetic energy. Temperature is a measure of the average kinetic energy of the particles in a substance. All substances have thermal energy due to the motion of their particles and the distance and the attraction between those particles. A substance's thermal energy depends on factors such as the type of matter, the amount of particles, the substance's temperature, the substance's state, and the substance's volume. Thermal energy is transferred between objects at different temperatures. When an object and a system are at the same temperature, the system is thermal equilibrium. So when they're all at the same temperature, it has reached thermal equilibrium. Okay, so let's just review some of these vocab words we talked about. Kinetic energy is the energy an object has because it's moving. Potential energy is stored energy. So kinetic is in motion, potential is at rest or stored. Temperature is the average kinetic energy of the particles that make up a material. As the temperature of the material increases, the kinetic energy of the particles increase. So the more kinetic energy, the hotter the substance is. Heat is a movement of thermal energy from a warmer object to a cooler object. So heat is going from warm to cold. When thermal energy moves between a material and its environment, the material temperature changes. Heating continues until all objects in the contact are at the same temperature. This is known as thermal equilibrium. Okay, make sure you keep your notes, and that is all for today. Have a good day.